Greetings, class, and welcome to Week 10. This week, this is CIS 4670, Week 10. We're going to be looking at cryptography in Chapter 8 of the book. We also will have Lab 2 due this week. So if you have not gotten that done, please look at that. That is going to be due November the 2nd. Weekend of November the 2nd, I should say. But again, please check your syllabus for the correct date, or feel free to ask me. So anyway, let's go ahead and jump into cryptography. Cryptography is one of those areas that can be extremely difficult for some or very easy for others, depending on when you learn it, to be completely honest. I learned cryptography as one of the first things in information technology before I learned microcomputing back in the 1990s. I learned cryptography as a mechanism to securing voice traffic over radios in the military. And some of the fundamental, foundational elements of cryptography translate over into the world today. Things such as authentication, hashing, algorithms, etc. It's all the same. It's just gotten more complex because we can do higher end calculations, giving the speed of the microprocessors at our disposal. So that was a mouthful. So in this chapter, we're going to compare and contrast different types of attacks on cryptography, as well as look at the basic concepts of cryptography. Explain what a cryptographic algorithm is and their basic characteristics. Then in typical CompTIA Security Plus fashion, you're going to be given scenarios in your questions on your quizzes and stuff on how to install and configure wireless cryptography and how to implement public key infrastructure, or PKI for short. So let's get started. So cryptography is old. It's as old as humankind itself. And a lot of cryptography is just understanding how to take something that is plain, make it complicated, and then be able to reverse it back to plain. So, for example, taking plain text, putting it through a mathematical process, making it ciphertext, and then being able to reverse that and making it plain text again. That is the basics of cryptography. So there are different types of ciphers or ciphering that allow us to do that. There's substitution ciphers, which is a type of code that changes one character or symbol into another. So for example, you take an A and it is now a G, or a B and it is now an H. And then there's transposition ciphers, which involves transposing or scrambling the letters in a certain manner. So this is where we get more in depth with mathematical calculations in order to make an A an F, and then the next iteration of an A Z. All right, but we have back-end mathematical calculations that we can reverse in order to take that transposition cipher and take the ciphertext and make it back into plain text to the original calculation that it was through the mathematical schema. That's a mouthful. I know it sounds really complicated, but when you break it down into its component basic parts, it gets a little bit easier. There's a lot of other definitions that you see throughout the chapter, and some of the ones that we have are here. Pay particular attention to what hashing is and mathematical cryptography. So hashing is, you're going to be using it throughout your career in information technology and in information security. And it's basically performing a calculation on a message, say like a password, and converting it into a numeric or alphanumeric hash value that is hard to crack. There are some hashing algorithms that are easy to crack. They have certain telltale signs, and then you can reverse them very easily. So such things as authentication hashes, like what are used in WEP, in wireless, that is very easy to reverse. Older versions of hashing technologies like RC4, very easy to reverse. Why? Because the mathematical calculation is known, and then putting all the permutations through a key space goes relatively quickly, and there's a lot less guessing that is involved with it versus newer hashing algorithms such as SHA-256, for example. So, one thing to take away from this lecture is the difference between symmetric algorithms and asymmetric algorithms. Symmetric algorithms are very simple. They require both ends to hold the same key. Think of a key as a password. So, in order for you to encrypt and decrypt data on both sides of a communication channel, you have the same key. Each end has to have the same key to encrypt and decrypt. So that's not as secure as asymmetric, which we'll talk about in a moment, but it is very fast. It is less complicated. It is easy to implement. Additionally, you can see some common standards that use symmetric cryptography or symmetric algorithms, such as DES, triple DES, AES, CAST, and GOST. So these are, again, widely used, and some of them are secure. AES is still federal standard, and it's still a FIPS standard, and it can be is widely used in things such as WPA, WPA2, and a lot of wireless encryption. Asymmetric algorithms provide a solution in which you can use key sets. So you have a public key and a private key. And depending upon the system, a public key will either encrypt or decrypt, and a private key, again, will either encrypt or decrypt. Again, when I say the system, with PKI, you encrypt with your public key, you hand your private key out so that your user, customer, whatever, can decrypt that message. SSH is a little bit different. It's kind of reversed, and all that is basically semantics, nothing more than that. The concept stays the same. In order to have a full functioning two-way communication channel with asymmetric cryptography, you must have key sets for each individual person or station that you are communicating to. For example, if I'm going to have a communication set with Hansel, and one with Sarah, and one with Jenny, and one with Tom, I need 4 key sets because I need a key set from each of them. Now I need a 5th key set so that I can send them traffic. So I can use the same public key private key set for all of my users, but I will have a different public key private key set for each individual user that communicates back to me. I hope I explained that very well enough. Now, can I have a different key set for each individual user that I communicate to? Absolutely. That just increases the number of key sets that I need to have. The more key sets, the harder it is, the more secure the system is in practice. Cryptographic algorithms are used typically to look at messages from an unencrypted or clear text state and get them into an encrypted message. So an algorithm, all it is a mathematical problem. And we basically take a string of text, right? Put it through this mathematical calculation, and we get the encrypted text out the other side. Hashing is similar to that in concept, but it is converting a message or data into a numeric value. So we're looking at a numeric value there. So some good hashing algorithms are the SHA and the Message Digest series. There are also rainbow tables with salts, and you have the ability to do key stretching. So I'm going to pause right here because I want to go over what a salt is. So what a salt is basically is an additional metric, and I pulled up the Wikipedia page here for it. So in cryptography, a salt is a random data set that is used as an additional input into a one-way function that hashes the data password, passphrase, whatever. And they're used to safeguard passwords while they are in storage. So historically, passwords were stored in plain text on a system. Obviously, we don't do that anymore. But over time, they were hashed. But hashes were able to be broken very easily. And now what we're doing is with a salt, we are adding an additional value into the algorithm. And the salt value is randomly generated, all right, and can be any length. In the case of a salt value, which is say like 8 bytes long, like in this example, the value is appended to the plain text password, and then the result is hashed. So you're taking the salt value and you're padding it. You're padding it onto the end of the password. So you see here the string to be hashed. We have an additional data set right there. All right, we have the same password, but then we hash it and we get a hash plus salt value. Now, more modern hashing algorithms will not only have a salt value, which is randomly assigned, we can also add what is typically called a pepper value. So it could be a control set, which is the same value, but we add that again onto the end of the string. So there, what we can do is we look like we give it a pad, and we can actually trick a lot of common programs like John the Ripper and prevent them from reversing or cracking our hashes if they are ever compromised. Rainbow tables, this basically makes rainbow tables useless, as the salt property is hard-coded into products, and new rainbow tables can't generate a salt. So that's the benefit of using salted hashes, in that it makes your passwords so much stronger at rest. So it's a good segue into code breaking techniques. So code breaking techniques are going to involve looking at blocks of encrypted data and encrypted messages in order to determine if any common patterns exist. Algorithm errors are typically within the program itself that's used to perform a task or instruction. And brute force attacks are programs that are used in order to try to crack passwords, or actually crack hashes, or reverse them. And then there's always the good old human error, where we would use something like social engineering or social engineering techniques in order to get information, in order to help us break a code. A cryptographic system is basically a computer system or process that is used to provide encryption and decryption. So a cryptographic system, for example, might be a VPN. Confidentiality and strength with that go into its component parts, what algorithm it's using, what hashing value, what's its key set, things like that. They provide integrity for digital signatures, as well as authentication and non-repudiation, meaning that you cannot dispute who you are. So where does this all come from? Well, a lot of early cryptographic standards were designed or used in warfare in order to help the government or the military secure communication between units. Government agencies that kind of work greatly with cryptography, not only in developing new cryptographic methods, but also trying to break cryptographic chains from, say, other governments, would be the National Security Agency. The NSA and their Central Security Service are kind of the go-to people in the national security apparatus that does this. So also a lot of the science behind this and the scientific arm of the NSA is the National Institute of Standards and Technology. They do a lot of other things too, but they also write standards for cryptography for commercial use. Let me emphasize that, commercial use. All right, so we'll get into PKI, public key infrastructure now, and all PKI really is, they use the X.509 standard. It's a system that allows us to create, manage, revoke, and delete cryptographic keys for some purpose. There are public key infrastructures, and there are private public key infrastructures. Public good example of a public key infrastructure would be a registrar like GoDaddy, or some other type of organization that you can create a digital certificate with, or a certificate for a website, because that's basically what we're using when we get that little green lockbox on our browser that ensures us that, hey, all of our traffic is encrypted when we're doing banking online, for example. Public key cryptographic standards are a set of voluntary standards that are created by RSA, which is proprietary, and other security leaders, and they're typically used for public consumption. Kind of staying with this, understanding the different standards, X.509 is kind of like the gold standard for public and private key creation. But it also defines procedures that should be used to distribute public keys, like how many servers, what type of servers we're going to have. TLS, which works on the old secure socket layer. You guys remember that? TCP port 443. It is used in order to establish communication between a web browser and a website. So when you go and you bank online or you order something on Amazon, you should be using this. Your browser keeps it in the background, and of course you're kind of a little bit unaware. It's only you have to be worried about it when you don't have that lockbox, it's broken, or it has a red line through it, that you should question it. Also, you can also look up the certificate information if you're really unsure as to the security of the channel, and you can look at the information from there in your browser. SMIME is used for secure mail, encrypted mail. This is getting a lot more traction, especially as we go to cloud mail providers like Gmail or Office 365. So there are some standards that we see and some acronyms that we use. PGP is a good one. Pretty good privacy. It is a freeware. Actually, it was free, then it was proprietary because somebody bought it, and then it went back to being free again. It's a way to not only use email encryption for, say, attachments, but you can pretty much encrypt any kind of file you want, but typically it's used for attachments. HTTPS, which is SSL, or now TLS, which secures browser to server, web server traffic. And Secure Hypertext Transport Protocol, SHTTP, which is basically a secure version of HTTP. And then we have the gold standard for VPNs, which is IP security, or IPsec. You use IPsec in most of your modern virtual private network deployments, and understanding the IPsec stack is very similar to understanding the OSI or TCP model layers. So, with that in mind for VPNs, we basically have to have a tunneling protocol that sets up a secure channel between two endpoints, whether it's a browser-based VPN, like a lot of times you get with Tor, or like a NordVPN, or a station-to-station, a point-to-point VPN, which you would get with two routers or two firewall appliances. This adds capability to your network, and a lot of common protocols that work at layer 2, which is where this is set up, are point-to-point tunneling protocol, layer 2 forwarding, or tunneling protocol at layer 2 tunneling protocol. These are all FIPS standards, and what the Federal Information Processing Standard Guideline is a guideline, a standard, information put forward by the U.S. federal government as to what are secured protocols and methodologies for government information systems. Oops. Skipping around here, I apologize. Alright, here we go. Slide 15. Public key infrastructure is intended to provide a way for securing messages on a very large scale. So take the entire internet, for example. All of our registrars that we have, the GoDaddies of the world, and Amazon is their own registrar now, and the other ones that are out there, like Layer 3 is a registrar, they all provide certificate authorities. They can make up certificates for you. They have a root authority to do so. So if you needed to buy a certificate for your website in order to make your website secure, you would go through them in order to purchase it. They could be good for 1 year, 2 years, 3 years, 5 years, depending on how much money you wanted to spend. Typically, you don't want to do a certificate for more than about 3 years, because then it's a diminishing return, because your crypto has been out there for so long. You have to worry about it being compromised. RSA is typically the encryption algorithm that is used in digital certificates, and you have two types of authorities in creation of certificates. You have your certificate authority and your registration authority. Your registration authority is basically going to be like your GoDaddy, and your certificate authority is going to be whatever server that they are using in order to check it for when browsers go to your website in order to encrypt traffic. That is basically an identity step to prove who you are. So we also have some definitions here on slide 16. Your certificate authority, which is an organization that is responsible for issuing, revoking, and distributing certificates. A registration authority, which can distribute keys, accepts registrations, etc. And then your local registration authority, or LRA, which can be used to identify or establish the identity of an individual for certificate issuance. So can you prove who you are, basically? Implementing certificates can be very cumbersome and very time-consuming, especially if you do not have the process down, and it depends on platform as to how easy or hard it is going to be. You have a lot more steps typically when you're doing this on a web server for Linux than you do with a web server for Windows. You have more steps that you have to do in Linux-based load balancers, for example. Whereas with elastic load balancers in Amazon Web Services, AWS, it's like 2 buttons and an upload and you're done. So there's different levels of complexity. Some vendors, like Amazon, like Azure, like Google Cloud, have made this process so easy. They've taken a lot, but in essence, they've taken a lot of control away from the administrators. So keep that in mind. Certificate policies define what a certificate can do, and basically who can use it, or what type of system it can be used on, I should say. A detailed statement of the CA is used to issue certificates and implement those policies. Certificates do not last forever, so we have to have a revocation policy, which basically means the certificate expires and it's no good. Now, we can self-expire a certificate, meaning that I can go into a system and go, okay, this certificate has been compromised, or I don't want to use it anymore, I want to get new ones, and I can revoke it. Once I revoke that certificate, it can no longer be used, and then you start getting errors on your web page if you still have it tied to your web page. This goes into a certificate revocation list, or CRL. And this is just a list of revoked certificates, so they cannot be used again if they are stolen. There are online certificate status protocols. This is used in order to communicate the certificate viability from system to system. And then there's the repository, or a database, where the certificates are stored in their eternity. Now, what a lot of certificate authorities are doing is, once they revoke a certificate, they'll keep it for a few years, and then after that, they delete it and it's gone. And if a certificate is tried to be used again maliciously, it's just going to show up as a like a self-signed cert at that point in time. And last but not least, we have trust models. So trust models are used with PKI. They're hierarchical, bridged, meshed, and hybrid. So in the book, read through these. Hierarchical are the most common. Bridged are probably the least common. Meshed, you see a lot in mid-sized organizations, and a hybrid is just a combination of any of the three. Your hierarchical model is what's being used on the internet today with the registrars all the way down to the web servers. Okay, so furthermore, hierarchical trust models, also known as a tree, a root CA, top, down. Again, like I said, a bridge trust model. That's a typo. I apologize. It's supposed to be bridged trust model. Is peer-to-peer relationships between a root CA and a client. A mesh expands the concept of the bridge model by supporting multiple paths, and a hybrid is a combination there of any two of those above. So that's going to conclude Chapter 8 here for Week 10. And we'll cover or finish up Lab 2 this week. And then Homework 4 will be due next week. We'll be looking at that. That is the write-up that you have to do on the USC lecture from Malcolm Nance. So be looking for that as well. So until next time, this is Dr. Brown signing off. We'll see you around.